Alright, welcome back. We're going to continue our lectures on stoichiometry. This lecture is on chemical calculations involving balanced chemical equations in the mole ratio. In your text, it's page 271 to 274. By the end of this lecture, you will be able to perform calculations using balanced chemical equations to determine the quantity of substances used or produced in a reaction. And so the first thing we'll do is just remind you what a balanced chemical equation actually means. And so if we take a look at this balanced chemical equation, it's balanced at a ratio of 1 to 3 to 2. And what that means is we could say that there's one molecule of nitrogen gas. When it collides with 3 molecules of hydrogen gas in just the right way, we end up with 2 molecules of ammonia. And if you take a look, if you just count the atoms, there's 2 nitrogen atoms as reactants, there's 2 nitrogen atoms as products, there's 6 water molecule or hydrogen atoms, and our products, there's 6 hydrogen atoms. It's just now there's 3 attached to each nitrogen. So balanced chemical equations are balanced for the total number of atoms in a reaction. And it can be read as a molecular reaction in terms of molecules plus molecules plus molecules, but we can change that to calculations of moles plus moles plus moles. And because a mole is really just a certain number of molecules. It's 6.03 times 10 to the 22 molecules. So we can balance it or talk about things according to a mole. If we look at the mass is conserved. If you look at 1 mole of nitrogen gas, 1 mole of nitrogen gas is 28.02 grams. That's the molar mass of nitrogen gas. And if we look at the molar mass of water, hydrogen ions, or hydrogen atoms, molecules. So if we look at hydrogen molecules, each molecule weighs 2.02 grams per mole. So 1 mole. So if we look at 1 mole of H2, it would be 1.01 grams. Since we have 3 moles, we have to multiply that 1.01 by 3. So that's how we get the 6.06 grams. When we take a look at the amount of ammonia that would be produced, it would be the 2 masses added together. This 34.08 grams is the same as 2 moles of the gas. 2 moles would weigh that amount. We could double check it using our molar mass formula. So, and it should make sense that the total mass of reactants has to be equal to the total mass of products because we conserve mass through chemical reactions. And so stoichiometry is Greek. It's set for a series of steps for measuring something. And so that's the definition of stoichiometry. It's used in chemistry, and with stoichiometry we can calculate the mass, concentration, or volume of any chemical compound in a reaction if we know the mass, concentration, or volume of any other compound in that reaction. And it can be any one. It doesn't have to be a specific one. So as long as we know the concentration, volume, or mass of one thing, we can find the mass, concentration, or volume of any of our other reactants or products. The first step in each stoichiometry is to convert your known measurements into amount in moles. And the reason we do this, let's go back a slide, is all of our chemical reactions are balanced according to moles using simple whole number coefficients. So because our chemical reactions use these nice whole number coefficients and they're related to the number of moles of substance, we need to convert all of our measurements into moles when we do our calculations. So that's why we have to find moles, and then we use something called the mole ratio. So here's an example of what we're talking about. Here we have a compound. It's called malachite. And it decomposes into copper 2 oxide, carbon dioxide, and water. And this would be the balanced chemical equation for the decomposition of malachite into those compounds. When we look at it, here's what we can say. We can say that for every 1 mole of malachite that decomposes, we get 2 moles of copper 2 oxide, 1 mole of carbon dioxide, and 1 mole of water. We can write that as a ratio. We can say the ratio would be a 1 to 2 to 1 to 1 ratio. So for every 1 mole of malachite, we get 2 moles of copper 2 oxide, 1 mole of carbon dioxide, and a mole of water. And we can talk about any set of 2 using this ratio. We can talk about the relationship between malachite and copper oxide. We can talk about the relationship between carbon dioxide and copper 2 oxide, or between water and malachite. Any set of 2, we can talk about the relationship. And here's how we'd use it. So, if we want to figure out how much copper 2 oxide will be produced when 2 moles of malachite are decomposed, we do the following. And we should add a question mark to that question. There we go. So, there's our balanced chemical equation. And now we're going to find out, we want to find out the number of moles. And so here's, when I'm using these equations, here's what I do. I want to find out, first I find out what I'm looking for. I want to find out what amount. Amount is always measured in moles. And the symbol for moles in all of our chemical equations is N. So we're going to do that. So I want to find out the N, of copper 2 oxide. And then I write down any numbers that I have in my equation underneath the substance they refer to. So I have copper 2 oxide. That's what I want to find out when 2 moles of malachite. So I know the N of this substance is 2 moles. And now I can use my mole ratio to answer my question. And here's what we're going to do. We're going to go with the N of CuO is equal to the number of moles of CuOH2 CuCO3 times my mole ratio. And here's what I want to find out. Right now, I know the number of moles of my malachite. And so the mole ratio I'm going to use is I'm going to set up like this. With the mole ratio of my unknown, so it's number of moles of the unknown divided by the number of moles of my known. So that's the basic formula I'm going to use. And so it would be the number of moles of malachite. So that's going to be 2.00 moles. That's how much I'm actually reacting. My mole ratio, these come from the coefficients of the equation. And so I have 2.00 moles. The moles of unknown, the thing I'm looking for, is 2, because that's my copper oxide. I'm grabbing it right from here. The number of moles of my known is 1, right here. I have 1 mole of copper or of malachite decomposes. When it does, it forms 2 moles of copper 2 oxide, and so 2 times 2 over 1 would be 4. So that's the number of copper 2 oxide formed when I decompose 2 moles. Alright, let's try another one. So we want the amount, and the word amount always refers to moles. If we want to find mass, we'll ask for mass. Or if we want to find grams, we'll ask for mass. If we want to find volume, we'd ask for maybe milliliters or liters. So amount always refers to moles, the amount in moles. So one amount of iron 3 oxide is required to produce 1.5 moles of iron from the following reaction. So they gave us the reaction again, and so I'm just going to fill in my numbers underneath the things that I'm trying to find. So we want what amount of iron 3 oxide is required. Iron 3 oxide is over here, so this is what I'm looking for. and this is what I'm given, iron solid. So I know this is equal to 1.5 moles. That's how much was actually made. And so we're going to say the number of moles of iron, oops, let's try that again. The number of moles of Fe2O3 is going to be equal to the number of moles of iron times my mole ratio. And again, it's going to be unknown over known and again, these come from our reaction coefficients or equation coefficients. And so we're going to say the number of moles of iron. Well, we know that we were able to get 1.5 moles of iron, and our coefficients of our unknown over known. So our unknown would be again a 1. Our known this time is a 2. So it's going to be, well, I'm just going to change this a little bit so you can see some unit cancellation. So I'm just going to erase my multiplication sign here for a second. And what we really have is we can say this is 1.50 moles of Fe. That's how much was produced. When we set up our mole ratio, we want to change our units so that we have moles of Fe2O3. So that's the units we want because that's what the question asked for. So we put that on top of our ratio. We don't want the moles of Fe, so we're going to divide by the moles of Fe. And again, these are both from our equation coefficients. So these are still the equations from the coefficients. I just wrote it down a different way. If you don't like this way, then you can ignore it and just do it the other way, but they give you the same answer. And so we go for our coefficients. The moles of Fe2O3 is 1. The moles of Fe is 2. And so we're going to multiply the number of moles by a half, or multiply by 1 and divide by 2. And we end up getting 0.75. And if we check our units, moles of Fe, we'll just write this as a fraction. We have moles of Fe on top. Those cancels with the moles of Fe on the bottom on the other side. And we're left with moles of iron 2 oxide, which is good because that's what we want. Sorry, iron 3 oxide, because that's what we want. So moles of Fe2O3. And you can write it down behind the equation, or if you prefer to write it down with a notation, you have to have either this or this written down in your answer. Otherwise, I don't know what moles you're talking about. We can measure all 4 of the compounds in this equation and find out the number of moles of any of them. I want you to tell me what you found the moles of. So you have to have either of these notations. You can say moles of Fe2O3, or you can use the mole notation. Must use either. So we can say use either one or the other. But you have to have at least some kind of indication on a written question as to what you've actually told, what you're actually producing as an answer. Alright, one more example here. We want to determine the amount of carbon dioxide produced and the amount of oxygen required when 200 millimoles of butane are completely combusted. And this time they didn't give us a formula, so we have to make one on our own. And we know that butane is C4H10 gas. If we're combusting it, then they're telling us the type of reaction we're doing. It reacts with oxygen. And now we've got to predict our products. And our products are going to be carbon dioxide and water. And now we're going to balance our chemical equation. I'll balance my carbons first. I know I'm going to need 4 carbon dioxides to balance my carbons, for my waters, I have 10, or for my hydrogens, I have 10 on my reactant side. I need 10 on my product side, and then I count up my oxygens. So I have 8 O's here, and another 5. So that gives me 13. So I'm going to need 13 over 2 in front of my oxygen, and now I'm going to double everything. And so, on a piece of paper, this is why you work in pencil, and then you can just erase the coefficients as you go through them. So, I know I need, where does my pen go? I'm just going to write my reaction underneath just to avoid the erasers. So we're going to balance it by doubling everything. So 2 C4s, H10s, plus 13 O2s, go to form. And for doubling it, it would be 8 CO2 gas plus 10 H2O, and that would be liquid. Don't forget your states. Otherwise, it's just wrong. If you have no state, if you're missing one state, that's enough to get the balanced chemical equation wrong. So always have your states, always have them balanced. And now we'll fill in what we're trying to find out and what we're looking for. So we want the amount of carbon dioxide. So we want an N there. We want to find out also the amount of oxygen, so we'll put an N under our oxygen. We're given the number of moles of butane. 200 millimoles. I always like to work in moles, so I'm going to say that this is the same as 0.2 moles. And now we have two things to find out. And so we'll start with the one that's closest, only because it doesn't really matter. We can find oxygen first or carbon dioxide first. Either one is going to require the use of our mole ratio and butane. So the number of moles of O2 is going to be equal to the number of moles of C4H10 times the moles of my unknown for oxygen would be 13. So we can put mole O2 over the mole of C4H10. Again, these are the coefficients from our equation. We'll just plug them in, and we get, so the number of moles of methane is 0.2 moles. That's how much we actually used, times the moles of oxygen would be 13 from our chemical equation over 2, because that's the coefficient for butane. So we multiply by 13, divide by 2, and we get 1.3 moles, and that's the number of moles of O2. And now that we have the number of moles of O2, we're going to find the number of moles of carbon dioxide. Now, we can use either the answer we just found or the information that was given. I always like to use the information given just in case a mistake was made with our calculation. So we should get the same answer, and maybe we'll do both just to show you we get the same answer. So this is moles of CO2 over moles of C4H10. And so we're going to get 0.2 moles times the moles of CO2 is 8 over 2, which is the same as multiplying by 4. So 0.2 times 4, and we get 0.8 moles. This is the number of moles of CO2. So, there's our calculation. Now, if we had used, this should be equal to the number of moles of C4H10 times our moles of we'll try this one more time. So I just want to show you that if we had used our answer for oxygen, we still would have gotten the same answer for carbon dioxide. So this is the same. We could say this is the same as we could use the number of moles of oxygen, but now our mole ratio would change. We'd be using our moles of CO2 over our moles of oxygen. And so NO2 we said was 1.3 moles. And this time we're going to multiply it by 8 over 13, because that's the mole ratio between carbon dioxide and oxygen in our balanced chemical equation. It's an 8 to 13 ratio. When we take our 1.3 times 8, divided by 13, and we get 0.8 moles. Sorry, 0.8 moles. One more thing we should talk about, we still have to worry about significant digits. Technically in this question, we have 3 sig digs, and we're working in millimoles, so we should report both of our answers the same way, with 3 significant digits or in millimoles. So for my NO2, I would say 1.30 moles to get my 3 sig digs. For my N, CO2, probably the easiest way would be 800 millimoles. The other way we could do it would be 8.00 times 10, and I guess it would be to the negative 1 moles. So any of these would be the best way to report the answer. I would probably stick with the first two, just because they are the easiest to require the least amount of writing. So there are some examples on page 258. Give those a try, and we'll do some more chemical calculations in the next lecture.